Good morning, guys. This is module 1 in CPP of S3 Chemical Engineering. So, the important concepts included in the module 1 are the introduction to unit operations and unit processes, how they differ from each other, and some of the examples. Then, units and dimensions. Then, we have the concept of moles, uh, which include molarity, molality, normality, etc. And then, we have the ideal gases and the real gases, the equations used to find out for both equations used for both ideal and the real gases. Then you have the other equations of state for real gases such as the RK equation, the PR equations, etc. Then we have the concept of gaseous mixtures and the introduction to average molecular weight for these mixtures. So moving on, the first topic is unit operations and unit processes. So as already written, a unit operation is one which involves only a physical change. Physical change is mainly referred to as the one where there is a phase change between the reactants and products. For example, if we think of a process like evaporation, the reactant which we take is liquid and the product which we finally get is is in the gaseous state. So that is an example of a unit operation. Most of the processes used in the chemical industries are unit operations. Because some of the basic ones are evaporation, drying, absorption, distillation, etc. And the unit processes, as said, are those which are related to chemical changes. So both the chemical nature of the reactants and products will be different. The examples include oxidation, sulfonation, alkylation, etc. So moving on to the next concept, we have the units and dimensions. So this is something that we have been using for a long time. So unit as shows as written is how you define a quantity. For example, if you're taking mass as a quantity, we define it as in kilogram. If you're taking the quantity as speed, it is defined in meter per second. So units is divided into two. You have the fundamental units and the derived units. Fundamental unit, as we know, it has seven. It is divided into 7 units. It is like 7 of them. There are 7 of them. We have the length, we have the temperature, we have the amount of time, etc. And then comes the derived units. So these derived units are the one which are derived from the fundamental units. For example, if you take force, which is the SI, which is force, which is a product of mass and acceleration. Mass, we have the kilogram, which is a fundamental unit, and then we have speed, which is meter per second. I mean, not speed, we have acceleration, which is meter per second square, which is also from the fundamental unit. So we get another derived unit called as Newton. So the common system of units that we use are of 3 types. You have the CGS, FPI, and the SI. We mainly use the SI system nowadays. The CGS consists of the centimeter, gram, second unit, and the FPS is the British unit, which is the foot, pound, second, and the SI is a system international, which we use now. So in this topic, it is also important to know the conversions. For example, like you have to convert from kilogram to pound, or from centimeter to foot, or your meter to foot, some things like that. Well, the conversion is also important. Well, you don't have to remember these or the values for conversions because it is there in the calculator. So know how to use a calculator. And the next important topic is the conversion of equations. This is important because this is an actually important topic. So the question will be as given. Explaining what the question is more easier. So you have a given equation like h equals 0.026 g power 0.6 by d power 0.4. The given system of equations are in the FPS unit, where h is the convective mass transfer coefficient, g is the mass flow rate, and d is a diameter. So we have the units of all the three h, g, and d. So the question will be convert the given equation into an equation where all three H, G and D are in the given set of units. So moving on to the solution, we have, so initially we have G in this above unit, in the FPS units, and we have, when we define the G dash to be in the new units, like that is gram per minute centimeter square. So we have G in the FPS unit equals G dash in the new units. And as we have said before, and as I've said before, you need to know the conversion of how to convert gram to pound, minute to hour, and centimeter to feet. It is there in the calculator. You just have to plug in the values, and then after converting, we get the value as G equals G dash into 122.92. And similarly, if we do for D and D dash, we just have to convert from centimeter to feet. So we have D equals D dash by 30.48. And similarly for H2, we have H equals H dash into 122.69. So we have the relation between the old and the new H and the H dash. So now we have to just plug in these values in the original equation so that we get the new equation in the H dash, G dash and the D dash terms which we have defined in the new units. So plugging in the values, we get the new equation as H dash equals 0.0149, G dash per zero point 0.6 by D dash per zero point 0.4. This is a very important question, and I've seen mostly all the question papers contain one question like this. Okay, so now moving on to the ideal gases. We know that an ideal gas is one which obeys the ideal gas equation, that is PV equals nRT. And we also know that no gas is actually an ideal gas. An ideal gas. A gas only behaves, all the gases that we have are real gases. Gas behaves as an ideal gas only at very low pressures and high temperatures. Okay, so we have the different forms of the ideal gas equation, like if you are replacing the number of moles with the weight by molecular weight, and then we have the weight by volume as density. We have the P into m equals dRT, where m is the molecular weight of the gas and d is the density. And here R is the gas constant. It is important to know how to derive the value of R in different units. For example, if you want to derive the unit of R in liter atm per mole Kelvin, we take pressure as 1 atm, we take the volume as 22.414 liters, and N as 1 mole, and temperature as 273 Kelvin. So on doing the calculations, we get the value of R as 0.0821 in the given units. And if you want to get into the above units, we just have to convert the pressure, which is in atm, to pascals, liter to meter cube. So that's it, we get the value in joule per mole Kelvin. Now moving on to the van der Waals equation. This is an example of an equation for real gases. The equation is P plus AN by V square plus V minus NB equals RT, where A and B are the terms or the van der Waals constants introduced. One is for the molecular intermolecular forces, and the other one is for the, and B is for the volume. So we have the value of A and B. You have A equals 27 into RTC square by 64 PC, and B equals RTC by 8 times PC, where TC and PC are the critical pressures and temperatures of the gas given. It will mostly be specified in the questions. This is the most widely used equation for real gas. And the other equations of state include the PR equation, the RK equation, etc. When you just have to know the equations, there will be no questions asked from them. Now moving on to the next topic, we have the specific gravity. The specific gravity is simply the ratio of density of object to the density of the reference object. Reference object which we mostly use is just water. So in most of the questions it will be given as a specific gravity is 0.8, and the question uh, would be required to do with the density. So the density of the object will be 0.8 into 1000, which will be 800 kilogram per meter cube. Next one is an important law in the module 1, where we have the Amaget's law of additive volumes. It is similar to the Dalton's law of partial pressure. Well, Dalton's law said that the sum of partial pressures will be equal to the total pressure. Similarly, in Amaget's law, we have that the total volume will be equal to the sum of the partial volumes or the pure component volumes of the gas present. So that is VA plus VB plus VC equal to A. So then there's a small derivation included. So for component A in the mixture, we have P into VA equals Na into RT. But for the whole mixture, we have PV equals nRT. So when we divide, we get the important equation relation as VA by V equals YA. That is, volume ratio will be equal to the mole ratio. This is very important. I mean, understanding this, that mole volume ratio equals mole ratio is important, because in most of the questions they will be set as the volume percentages. So from the Amaget's law, we can directly state that the volume percentage equals the mole percentage. Next comes the concept of the average molecular mass. The average molecular mass is mainly used for gaseous mixtures. Like for example, air. Air is a gaseous mixture of oxygen, nitrogen, and little percentage of argon. The formula for finding the average molecular mass is m average equals m by n, where n is the total number of moles taken and m is the total mass of total weight of the mixture of gases. Or we can use the formula as m average equals x1 m1 plus x2 m2, where x1 is a mole fraction of the gas, m1 is a molecular weight. And it's important to know the difference between the m in the first equation and m in the second equation. So for example, I'm just explaining the concept using a very small example. As we said before, air is a mixture of gases, and for mixture of gases, we define average molecular mass. So we have 21% oxygen, 79% of nitrogen by volume present in air. So as said before by Amaget's law, that volume percentage equals a mole percentage. So that is, if you have taken the 100 moles or 100 kilomoles of air, we have 21 moles of oxygen and 79 moles of nitrogen. So the total weight will be 21 into 32 plus 79 into 28, because 32 and 28 are the respective molar masses of oxygen and nitrogen. So according to the first equation, we have molecular weight average equals total weight by total number of moles. Total weight is 2884 kilogram, and the number of moles, as said first, is 100 kilomoles. So dividing, we get the answer as 28.84 kilogram per kilomole. I mean, the questions based on average molecular mass are very common, and they also will mostly ask us to find the density too. Density can be found out from this. Now the density equals mass by volume. So we have average molecular mass by volume. That is, for 1 kilomole, the volume is 22.414 liters. So for 100 kilomoles, the volume will be 100 into 22.414. Okay, this is the last topic in the module 1. We have the critical temperature and critical pressure. So critical temperature is referred to as the highest temperature at which a substance can exist as a liquid, and the corresponding pressure at Tc is called as the critical pressure. mean the critical temperature is actually a measure of how strong the intermolecular forces of the gas particles are. I mean, if the weaker the intermolecular forces, lesser will be the critical temperature. So more hard it will be to liquefy the gas. There was one more topic that I thought you would be already well known with, which is a concept of moles. To find the number of moles from there, to find the molarity, molality, normality, and the relation between molarity and normality. Simple concepts as the mole fraction and the weight fractions. So that is all.